So we have gone through in some detail regarding deformation in a fluid in the previous lecture, trying to understand that in a fluid the velocity gradient, the quantity that gives us a measure of the velocity gradient or the deformation in the fluid is split into a symmetric part and an antisymmetric part, and how the symmetric and the antisymmetric part respectively have different meaning in terms of how it is deforming the fluid. Now the goal of doing all of this is to actually connect the internal response of the fluid due to the deformation. So that is what we are basically trying to do in this exercise. Before we move on to conservation laws, we want to actually see that what would be the internal response of a fluid given that you have some deformation that is going on in the material. So for that we need to understand what is an internal response, and this brings us to today's lecture, where we will get introduced to this concept of a stress tensor. So we will first see that why is this a tensorial quantity and precisely an order 2 tensor, and then try to hopefully see some properties of this particular tensor. So before we think of this tensor, if I just consider any fluid, and let's say that there is a boundary that encloses this fluid, there would be two kinds of forces that would act in the fluid. There would be body forces and there would be surface forces. So body forces are forces that typically come from long range interactions. A classic example basically being gravity. So in the entire bulk of the fluid, we consider the fact that the gravitational field doesn't change. So because of that, we will actually have the entire bulk experiencing a certain force which comes from these long range interaction, that is the weight of the fluid. So if I want to write this down, for a volume element dV, the body force would be rho g dV. And if you integrate this over the entire volume of the fluid, you get what is the weight of that particular fluid. Surface forces are the ones which come from short range interactions. So in the early classes that we went through discussions regarding treating fluid from a molecular point of view, we were discussing about different kinds of interactions that are there. So when you have the interactions basically being short range in nature, they fall off very rapidly. The forces are something that decay off very rapidly. So effectively, the forces are primarily confined to the surfaces. So that gives us an aspect of what are the surface forces. So we are going to actually get a feel for what this surface force is. So I'm going to define a quantity that is, I'll use the Greek alphabet sigma to denote a surface force per unit area. Sometimes you might find in the literature this is also known as the traction vector. It's a vector, so it has three components. So at any point on a surface, this gives me what are the forces per unit area. So now we want to do a force balance. We want to actually study a force balance of a element of fluid, how we are actually going about doing it. But before that, if we think of any surface, I'll draw an arbitrary surface. The surface force at a particular point would be a function, so sigma would be a function of obviously the point in space at which you are finding it and the instant in time that you are finding it, but also because it is at a particular point in space, it would depend on the normal, the unit normal at that particular point in space. So on that surface, at every point there is a unique normal that is defined. So the surface force at that particular point, besides depending on the coordinates, would also depend on the normal. Now, if there is no force that is residing on that particular surface, then you can also draw a similar force on the other side, which would be sigma x minus n, because the normal is exactly pointed in the opposite direction on the other side of the surface. Imagine a membrane, so there is a normal that is pointing out. You will have an equivalent opposite normal on the inner side. So there would be a force that is acting on the inner side. So since there is no additional force that is residing, sigma, I'm just going to now use x and not focus on time anymore, because we are going to just look at things instantaneously. So sigma of the negative normal is going to be negative of sigma x comma n. This is just saying that the sum of these two surface forces would be 0. So you have a force that is acting on the one side or one face of a surface. There is another force which is acting on the other face of the surface. Since there is nothing that a force that is residing exactly on that particular surface, then sigma of minus n should be equal to minus of sigma n. Now with this, we are going to do an exercise of trying to do a force balance. So I have a coordinate x1, x2, x3. So I have drawn a tetrahedra. So imagine there is this tetrahedra that is at the origin of this coordinate system. And this tetrahedra is what I am interested in terms of doing a force balance. A characteristic dimension of this tetrahedra is delta. Delta is like a typical dimension of this tetrahedra, which means the volume of this tetrahedra is proportional to delta cube. The area of this tetrahedra is proportional to delta square. I am using proportionality because I am not bothering about the precise numerical factor. You can actually find the volume of a tetrahedra given that one of the faces or one of the sides is of length delta, and then go around and calculate. We are not exactly trying to arrive at that exact volume or exact area, but we know that if one of the sides were of length delta, then the volume will scale as delta cube and the surface area will scale as delta square. This is an important information. Now, let's label this O, P, Q, R. So, on the surface or on the face PQR, I am going to draw an outward normal N. So now, for the other faces which are basically not visible, the ones behind, which is, so here the unit normal is N. So on the face ORQ, the unit normal, which is, let me use, so on the face ORQ, which is not visible, the unit normal is minus x1, right? On the face OPQ, the unit normal is minus x3. It's the unit vector along the x3 but negative of it. Similarly, on the face OPR, the unit normal is going to be minus x2. Right? This is basically what we have here as the various unit normals for this particular problem. So now, if I am trying to actually find the area, so let's say for PQR, so area of PQR is A naught. So if area of PQR is A naught, then what should be the area of ORQ? So if I consider the face ORQ, which is pointing in the minus x1 direction, the area for that, if I label it as A1, the area should be A naught n dot x1, the magnitude, right? If you think of this as the area vector, you are projecting it along the x1 axis. So the magnitude of that area is A naught n dot x1. Similarly, for the area of OPQ, which if I call it as A3, this should be A naught n dot x3. And the area of OPR would be A2 A naught n dot x2, right? So with that, now we can do a summation of all the forces that are acting. So the summation of all the forces would be summation of all the forces that are residing on the surface and summation of all the forces that are in the bulk, surface and body forces. So let's just look at the surface force. So for the surface force, I have a force that is acting on, so I'll redraw this picture. I have a force that is basically acting on the face, which is, so I had PQR, okay, so PQR. So I had a force which is acting on the face PQR, which is sigma on this particular face, sigma I, or if I want to, and this multiplied by the area A naught, right? The force that is acting on that particular face is sigma I A naught. The force that is acting on the face ORQ is going to be sigma I, let me just make sure the notations are. So let me just, one second. So the force on face PQR is going to be sigma n and A naught. The force on face ORQ is going to be, so this is x1, x2, x3. To remind you again, this is a normal that is minus x1, this is a normal that is minus x2, and this is a unit normal that is along minus x3. So the force on face ORQ would be sigma minus x1, because that's the normal. The normal on ORQ is pointing in the negative x1 direction, multiplied by area, which is A1. Similarly, if I do this for the other face OPR, I have sigma minus x2 and A2. And for the face which is in the bottom, that would be sigma minus x3 a3. So the sum of all the surface forces, if I now add them up, I will have sigma n a0 plus sigma minus x1 a1 plus sigma minus x2 a2 sigma minus x3 a3. And we just saw that sigma of minus a negative of a normal is negative of the surface force of that normal. If you remember, sigma is the surface force, so sigma of minus n is minus sigma of n, which means I can write the total surface force as sigma n a naught minus sigma x1 a1 plus sigma x2 a2 plus sigma x3 a3. We have also found what is a1, a2, a3, etc. in terms of the normals, right? So I can write this now as sigma n a naught minus sigma x1, and if you remember, the area vector on the face ORQ A1 was actually A naught N1 dot X1, right? The area of this particular, let me just shade this face. The area of that particular face is related to the area that you can view PQR via the projection of the unit normal on the normal x1. Similarly, for the other one, you would have x2 a0 n2 dot, sorry, these are all n, not n2. There is only one unit normal here, which is n dot x1 n dot x2 sigma x3 a naught n dot x3. So, surface force is, I will take the a naught outside and I have sigma n minus sigma x1 n dot x1. So what I will do is I will write this as x1 sigma x2 x2 plus sigma x3 x3, this dotted with n. This is basically your sum of all the surface forces. Now what should this be equal to? This should be, so sum of all the surface forces plus the body forces should be equal to mass times acceleration, right? Now let's try to scale, see how this scales in terms of dimension. So we are basically looking at this tetrahedra which has a characteristic dimension delta, and recalling what we said, that volume will go as delta cube, area will go as delta square. So the surface force, which is proportional to the area, will be order delta square. The body forces, which is proportional to the volume, will be order delta cube. And the acceleration of the fluid, which again depends on the mass of the fluid, will also depend on the volume, and that should at least go as order delta cube. Which means if I take the limit of delta going to 0, I arrive at the conclusion that for a tetrahedra that is infinitesimally small, the sum of all the surface forces should be equal to 0. Okay, so this is the idea that we are doing, that if we shrink the tetrahedra, the dimension is vanishing, then the surface forces will be the one that will survive, because the body forces and the acceleration will go to 0 faster. They are delta cube, which means as delta goes to 0, these objects are going to vanish faster than the surface forces. So what will be left behind is the sum of all surface forces should be equal to 0. So that tells us that the term inside the square bracket that you have here is 0. So sigma the surface force at a particular point is now related to this object dotted with the unit normal. So from that relation, when we arrive at this relation for this infinitesimally small tetrahedra, what we find that the surface force at any particular point is related to this quantity, where if you look at this quantity will have sigma I x, this is the x1's j, sigma I x2 j, sigma I at that location x3 j. So you choose any coordinate system x1, x2, x3. What you have here is an object that is an order 2 tensor. So this tells us that the object that is actually of more fundamental interest, rather than being the stress vector or the surface vector, is what is a stress tensor. So the stress tensor basically gives us the surface force at a particular point where the unit normal is n. So in mathematical sense, you can think of the stress tensor as a linear mapping of the surface normals to the surface forces. So at any point on a surface, you draw any arbitrary surface, at any point on the surface there will be a normal, and there is going to be correspondingly a force that will act. The stress tensor basically relates the normal to the force. So this is the fundamental quantity that you get, that the object of interest, rather than being the surface force at a given point, is the surface tensor or the stress tensor. So sigma ij, if you write in index notation, times nj gives us what is the surface force per unit area at a particular point, or the traction vector. So for the stress tensor, the ith component, the first index, gives you the direction of force, and the jth component gives you the direction of the unit normal. So if you now write this out, as you can see, for any order 2 tensor there are 9 elements. So if you write down any of those 9 elements, let's say sigma 1, 3. Sigma 1, 3 gives you a force per unit area, because this has dimensions of force per unit area. So it gives you the force per unit area in the one direction for a surface that is oriented along the 3 direction. By oriented, I mean that if I draw the surface, if this is 1, 2 and 3, the surface is something like this. It's in the 1, 2 plane. It's parallel to the 1, 2 plane. The unit normal is pointing in the 3rd direction. So, sigma 1, 3 gives you a force that is basically, so this is the normal. This is the normal to the surface, and the force that you are interested in is basically in the 1 direction. So, sigma 1, 3 will be giving you force in a direction 1 for a surface that is pointing in the direction 3. So, this has 2 indices to actually work with. So, when we learn tensors, now you actually see that a tensorial representation is becoming essential when you are trying to understand a deforming medium, a continuous medium. Because on a given surface, the force is not always guaranteed to act along the normal to the surface. So, as you start learning about a fluid in motion, you will see that when a fluid is in motion, the force that acts at any point on a fluid surface is not necessarily always going to be pointing aligned with that normal. Because if you think of this particular surface, if all the forces were exactly along the normal, then all the fluid is going to do is basically a compression and expansion. I mean, there is basically going to be just things going in and out. There is a compressive force or there is a tensile force. So, at any point in the fluid, the only force component that you are dealing with is tensile or compressive. That is what would happen if your surface force was always aligned with the normal. So, the sign that we always say is that this is a convention. So, the convention that we follow is, if the force is aligned with the normal, which is tension, then it is positive. If the force is opposite to the outward normal, then it is compressive and it is negative. So, now we are relaxing this, or we are basically saying that in general, surface forces are not always going to be tensile and compressive. There is an additional part of surface force that will come in, where the surface force can be perpendicular to the unit normal, not necessarily aligned to the unit normal. So, this introduces an important idea that we will get forward, is the idea of shear. Shear is what we are doing in many scenarios in day-to-day life. You place your hand on your bench and you try to slide your hand. What you are doing is you are trying to shear the bench surface. If you push it down, if I press the bench down, I am basically applying a force and the bench gives me an outward reaction which is normal to the surface of the bench. But if I try to slide my palm on top of the bench, the normal is still the same. The normal hasn't changed. The bench surface is pointing vertically upwards, but I am trying to apply a sliding motion on top of that surface. This is what is new. This is what is completely new now that you are doing, and this is something that becomes quite crucial when you are thinking of fluid. Because this, as you will see as we go on, is going to be a mechanism by which you can do transfer of momentum. That on a surface of a fluid, if I try to apply a force, that force or that momentum gets transmitted to the bulk. Because you are trying to slide things, you are trying to slide stuff around. If you stand in a queue, let's say there are multiple queues which are standing and one of the adjacent ones start to move, then automatically the ones who are neighboring, they are also going to get nudged and you are going to get pushed. So that's a mechanism of a transfer of momentum that is occurring. So we will get into these ideas in more detail when we talk about viscosity and what role it plays. But right now this is an important concept that we are getting introduced to, the idea of a stress tensor. So, as I said, the stress tensor sigma ij will have 9 elements. It's a 3 cross 3 In a matrix formulation, it's a 3 cross 3 matrix, so it has 9 elements. Now, would it have all 9 elements or would it have fewer than that? So, right now we did a force balance. Other than force balance, we will now do a moment balance, which means for that same object, we will try to actually calculate what is the moment that is being generated. So, the moment can be generated once again. So, writing it in broad notation that I alpha or omega dot, which is basically the angular acceleration times the moment of inertia, will be the moment that is created from the surface force and the moment that is created from the bulk force or the body force. Now, before we do this calculation, we can use that same argument that we are interested in a tetrahedra which is infinitesimally small. So, the tetrahedra is infinitesimally small, how would these objects scale? So, I, if you remember, is the mass moment of inertia. So, as a scaling, this scales as mass times some dimension square. You can find the exact value for a given shape, but dimensionally it is mass times some length dimension square. And so we know that if the object has dimension of delta, mass would scale as delta cube. So the mass moment of inertia will be order delta to the power 5. So this object is order delta to the power 5. Now for the bulk contribution to the moment from the bulk, so what we have to do is we have to do a volume integration. So if you know that the moment, if you are calculating, the moment would be R cross F if you were just doing a point mass. If there is a point mass about a particular point, you want to calculate the moment, it will be R cross F. That is what you are calculating. But this is not a point mass. So what we have to do is we need to do R cross the force per unit volume rho dV. It's not a point mass, it's an extended mass. So if there is an extended mass that you have, you choose any point about the origin, that's the moment arm, and F is the force per unit volume. So it will be G, the acceleration in this case. So well, here I have used rho already, so F would just be the acceleration, G. If I don't have rho, then it would just be F dV. So in the case of weight, this would be rho G dV. Now, how would this scale with the size of the dimension, delta? dV is the volume. So that scales as delta cube. So I would have a delta cube contribution from the volume. The moment arm will give me another delta, which means the moment that is generated by the body force would scale as order delta to the power 4 at least. Surface force. So for surface force, you need to do the same exercise of calculating the moment R cross the force per unit area integrated over the area. Right? I have a force residing on the surface. This object has dimensions of Newton per meter square, whereas this one is basically Newton per meter cube. That is force per unit volume, the bulk force, which is rho G. Here this is surface force that we just encountered. So rho cross F integrated over the entire surface area. So now if you do a dimensional argument, this would be delta square, this would be delta. This is all scaling arguments. We are not going into an exact magnitude right now. We first want to make our life easier to see that do we need to carry forward all of these in order to understand the moment balance. Otherwise, we will do a lot of algebra and eventually come at the same conclusion. So let's make our life easier. Let's see that for a tetrahedra that is infinitesimally small, if I write down a moment balance, I will say that the sum of all the moments will be equal to moment of inertia times angular acceleration. So for an object that is becoming vanishingly small, the moment of inertia, the mass moment of inertia will scale with the 5th power of dimension. The moment that is coming from the body force will scale with the 4th power of the dimension. and the surface force will scale with the third power of the dimension. Which means when delta goes to 0, what will finally survive is that the surface moment should be equal to 0. Now our life is easier, or at least more tractable. We can do some work with this instead of trying to bother about what is the mass moment of inertia, what is the bulk contribution. So we can just forget all of that and just focus on the surface force contribution. So for the surface force contribution, and this is where again we are going to go back to our best friend, which is using tensors. So R cross F dA, this would be epsilon ijk rj, and we know this object, the surface force, which is Fk dA. But we just encountered what is the surface force. We learned that a surface force Fk is sigma km nm. We learnt about the stress tensor. So let's try to use the stress tensor. So if you use the stress, so this should be equal to 0. So if you use the stress tensor, then epsilon ijk rj sigma km nm dA, this should be equal to 0. Now this is where we need to take help from the divergence theorem. So the divergence theorem basically relates a volume integral to a surface integral. So if you have a vector field, let's say A, then dou vi dou xi, okay, v is not a good choice, I am using volume. So let's take, so I will take A for a vector field. So then dou ai dou xi dv is going to be ai ni dA. This is the classical form of divergence theorem that you are aware of. Now if instead of this being a vector, this could also be a tensorial quantity, which means if you have dou ji dou xi of aji dv, this is going to be aji ni dA. So the divergence theorem can be applied to any ordered tensor that you want. So the idea basically being that when you have the gradient in a particular direction, you replace it with the corresponding area normal or the unit normal. So now if you see, we have the surface integral here. So that is nm dA, which means I can write this as dou xm of the entire quantity. I'm using R, right? So let me just stick to R. Dou rm rj sigma km and then dv, right? Now epsilon ijk is a constant tensor, so I don't need to bother about it, so I can just take that out. So I have dou xm dou rm. R is, I mean, you have a volume and then you basically have the point on the surface given by the vector r. So you can use r or you can use x, but it's just, I'm just trying to be consistent of how I've defined it. So you have rj sigma km dA is equal to 0. Now let's do the derivative, use the product rule. So I have sigma km dou rj dou rm plus rj dou sigma km dou rm dA is equal to 0. Now this, what is this dou rj dou rm? So you can, if you don't know, you can just put values of j and m and check. Dou r1 is 1. Dou r1, dou r2 is 0. This is only true for Cartesian coordinate system. Okay, you have to also just keep this in mind. So when you are doing these for Cartesian coordinate system, when you do this dou r1 dou r2, we are dou r2 is going to be 0. Sorry, is going to be 1. Dou r3 dou r2 is going to be 0, which means this object is the Kronecker delta. So if this is Kronecker delta, sigma km delta jm, this becomes m is going to be replaced, m is the repeated index, is going to be replaced by the free index j. So this becomes sigma kj, and the other one is dou sigma km dou rm dA epsilon ijk. Now if you compare the two terms, the second term has an r that is sitting here, which means the second term is order delta smaller than the first term in terms of dimension. Once again, when it starts to shrink, the second term is going to go to 0 faster than the first term. You have a moment arm that is sitting there, rj. So for delta going to 0, you finally have a relation that epsilon ijk sigma kj dA is equal to 0. Now this should be true irrespective of whatever is the volume that you have considered, whatever is the surface that you have considered. Nowhere I have actually here tried to say what the shape is. It could be the tetrahedron that we were doing, it could be some other shape. It is agnostic of what shape you are considering. So if this is true for any shape that you are looking for that infinitesimal volume, that means this identity or this relation should be true for the integrand. The integrand should be 0. The integral is 0 irrespective of the domain of integration or the surface area of integration, which means that the integrand should be 0. So now you see epsilon ijk sigma kj is equal to 0. What does this mean? When would this be true given that you have some arbitrary stress tensor sigma kj? This has a repeated index j and a repeated index k. Epsilon ijk is the permutation tensor which is also antisymmetric about j and k. It is also antisymmetric about I and j and I and k, but for the purpose of the present discussion, what we find interesting is that it is antisymmetric about j and k. So the only way this is going to be 0 is if sigma was symmetric about j and k. The double dot product of an antisymmetric tensor would be 0 when what you are double dotting with or double contracting is a symmetric tensor. So what this tells us that sigma, the stress tensor, is symmetric. This is a very important relation that we have, that the stress tensor is symmetric, which means we don't need all the 9 components, we only need 6 components. So sigma 1 1, sigma 2 2, sigma 3 3, sigma 1 2, sigma 1 3, sigma 2 3, and here once again sigma 1 2, sigma 1 3 and sigma 2 3. You only require 6 component. The stress tensor is symmetric. This is a very important relation that you get, and this is again not specific to fluid mechanics. At this moment I have not drawn the connection between stress and deformation. That is where we will now say that this is a fluid. So this is in general true for any problem in continuum mechanics. And then you can ask a question here. Is there some assumption that I have made which will invalidate this symmetricity conclusion? We have concluded that it is symmetric. Our final conclusion is that the stress tensor is symmetric. And this started off by actually writing that the sum of the two moments, one from the surface and the other for the body, when equated to the angular acceleration times the mass moment of inertia, if the dimension shrinks, then finally what survives is that the surface moment is equal to 0. So the assumption that we have made that in the fluid, we have said there are body forces and they generate a moment. But we have assumed without explicitly stating that there are no body couples. I have not stated this, but we have assumed this. Otherwise, there would be an additional body couple that should be there. If there are couples that are there, if there are body moment or body couple that are actually present in the fluid, then you would not have this equated to 0, but rather it should be equated to that body couple. Now, when do you get something like this? When would this kind of a scenario arise? Because when you have body couple, then obviously you are not guaranteed to get the stress tensor to be symmetric. The stress tensor can have an antisymmetric component also. This would happen in two scenarios, at least two scenarios, that you can come up with more scenarios where you get body couples. One example is if you imagine that the fluid was a conducting fluid and it was made up of, let's say, tiny suspended magnetic particles. So a ferromagnetic fluid. So each of these tiny magnetic particles which are suspended in the fluid, they have their own moment. So you have a local couple that is there in the problem. So in which case, when you are trying to do this, derive this relation for the stress, what you need to account for that the fluid locally can have a couple that is present. So this can happen when you are treating problems which have an ability for local body couples. Ferromagnetic fluid being, or ferrofluid basically being one example. The other example, which is where you can take a little bit of liberty and apply fluid to study problems like granular flows. So granular flows are basically you have a big sand grain. So these are not small tiny water molecules or air molecules that we are thinking of, but you have like large sand grains. When you have a pile of sand, that is a heap of sand that is actually moving, flowing, sand dunes, etc. You can model them as a fluid-like system. You can treat them like a fluid-like system and do exactly whatever we are doing here in terms of finding their kinematics, finding their stress, etc. Now, if you think of these sand grains and if you zoom them in, each of these sand grains, as they come close to each other, they can bounce and collide. So if you have a dense granular flow, then these sand grains are coming and bumping against each other. Now, if they come and bump against each other, they collide and go back, they will have some kind of collision. You can decide elastic collision, inelastic collision. But what will not happen is that the collision of the two sand grains, which come without any spin, they will not gain any spin post collision. If you have two sand grains moving in a straight path, they come and think of two billiard balls or two balls of anything that is easy for you to visualize. They come and bounce. As they come and collide, post collision, they are not going to gain any rotation. The only occasion where they will gain rotation is if these are rough particles. Because we always see this happening. You take a cricket ball and you throw it. If it falls on a rough surface, it can get a spin. It can pick up a spin. So it can actually get angular momentum. It can pick up a rotation, even though pre-collision it was purely in a translational state. Because the surface roughness that is there enables it to pick up some rotation. So when you have rough particles, rough granular particles, again you will have this whole idea that what we have done here will be violated. In the duration of the course, we are not going to consider problems where stress tensor will be anything but symmetric. We'll always, I mean, this is the only time we are mentioning this, and after this it is kind of taken for granted. But it is important to know why it is symmetric, what assumption did we make, because it's not a very exotic problem where this assumption breaks down. There are going to be scenarios where it will break down, so it is important to understand this concept, that what leads to the symmetricity of the stress tensor. Because this is not specific to fluids, it's specific to any material that deforms, where you are defining the concept of stress tensor. So now we have the tool set up. So we understood two things today. One was that what is this object that we keep calling in fluid mechanics as a tensor, a stress tensor, what it exactly is. So we saw that a stress tensor basically is a quantity that gives you a force associated with a particular direction of the surface area. So we were able to actually see, again, if you think of it in a mathematical sense, it's a mapping of the normal at any point on a surface to the corresponding surface force. Because you take any arbitrary surface, there will always be a unique normal to a point on the surface, if you are thinking of simple surfaces, orientable surfaces, and at that particular point you will have a corresponding force. So the stress tensor gives you a way of relating that surface normal to the surface vector or the traction vector. And the second point we saw that, so the first one was the definition of the stress tensor, and the second one was the symmetricity of the stress tensor. So with this, we have now picked up as many tools that we have to go forward. So I'll stop here.